guys, it's Nicole here with another tutorial. Happy Friday, happy Friday. I hope you all are doing very well. In today's tutorial, we're going to talk about ones complement and twos complement data representations. So I decided to put both of these tutorials together because they're both very, very similar to each other. So with very slight differences in the rules. The cool thing here is if you could do one, you could do the other one. So let's get started. So before we begin, we're going to talk about what is the purpose of ones comp and twos complement? What is the purpose of these things that we call ones and twos complement data? Well, it's all about data representation. So we said in the offset binary tutorial that it's all about being able to represent positive and negative numbers. So this is another way that we can accomplish that. So to give you an example, and this will probably look familiar to anybody that watched the previous tutorial, if we have a Cartesian plot like we do right here, we said anything in the upper right quadrant is positive numbers, but all these other quadrants in the other three is going to be, it's going to need, so if I was to put a dot, for example, right here, my x and y coordinate is going to, my x coordinate would be -3 in this case, approximately, and the y coordinate is going to be 2. So any other coordinate except the upper right quadrant is going to require the use of positive and negative numbers, and that's what this is all about today. So what I'm going to do is let's start with a little Google here. Our friend Google. You can see I still have this up from the offset binary tutorial. So what we're going to do is we're going to look at, let's go back here. So we are going to go to Google and we're going to actually look at ones complement. So let's just take a look at, first we'll start with ones complement. What is it? So basically ones complement, if we look at the values here, you'll see that it's actually pretty straightforward. So it's a way of representing a binary number where, so the positive number is just a typical positive number. So in a ones complement number, the most significant digit is usually going to be your sign bit. So if it's a 0, it's going to represent a positive number, and if it's a 1, it represents a negative number. So let me see if they put this in here. So so you can see, like in this little example right here, these are your positive integers and these are your negative numbers, and you'll notice that the positive numbers are the exact opposite of the negative numbers. So you'll notice, like for example, positive 6 is 0, 1, 1, 0, and negative 6 is 1, 0, 0, 1, right? So basically, so I'm going to leave this. I'm just going to minimize that for a sec. So if we were to like take a look at this just real quick, so let's just take a look at what we're talking about here. So if we have positive 6, so I'm going to come over here and put a positive 6 number right here. I keep using this. This is the same number we use in offset binary. Now again, same thing as before. Least significant bit over here, we'll say over this direction, and we'll say this is our most significant bit over here. That's the highest part of the scale over here, lowest part of the scale. And again, this will be 1, 2, and I'm going to go with an 8-bit integer. I'll keep everything on a boundary. 4, 8, 16, 32, 64, and then 128. And that should be, now I'm going to double check because it is Friday and I am tired. So 1, 2, 3, 4, 5, 6, 7, 8. So we do have 8 bits there. So number 6, a decimal number 6, so base 10. We do it just like any other conversion. So in this case, 0 cannot go into 128. 128 cannot go into 6, rather. 128 cannot go into 6. 64 cannot go into 6, so we put a 0 there. 32 can't go into 6. 16 can't go into 6. And 8 cannot go into 6. 4 can go into 6, so we're going to put a 1 there, and we're going to subtract 4 from our original value, which is 6. That leaves us with 2. 2 does go into 6, or 2 does go into 2, rather. So we're going to put a 1 there. I'm going to subtract 2, and we're left with 0, which means there's nothing left. So 1 can't go into nothing, so 0. So for positive 6, our actual number is going to be, in this case, on a byte boundary, it's going to be 5 zeros, 5, 1, 1, 0. All right, so that's your positive number. So that's a positive number. So now remember, this is our sign bit over here. So over here, this little bit here, that's my sign bit. So that's my sign bit. So basically, a 0 in one's comp, so a 0 equals positive, and a 1 is going to be negative. So let's do that like that. So negative is a 1, right? So basically with a ones complement number, another thing that happens is if we have an 8-bit word, we actually lose some of our values, because this is going to be, this number here is actually going to be used for the sign bit, right? So we actually only have 7 values to actually use for numbers, right? So because this is either positive or negative. So that's why, so with an 8-bit word, that's why you'll see the total number of values that we could represent for one's comp will actually be 2 to the nth, like this. So where n is the number of bits, and then we subtract 1 from it. So we'd have to actually subtract 1 here. So we have to go, actually, oops. So it'd be like this, minus 1. There we go. And if we do that, so 2 to the 8th power minus 1. So, and 8 is there because we have an 8-bit word total. Minus the sign bit gives us 2 to the 7th power, which is equivalent to 128. So basically we have base 10 there. Oops. There we go. So basically we have 128 possibilities. So we can represent the numbers 0 through 127. So essentially 128 total possible numbers could be represented with these 7 bits over here. So that's our possibility. So we have a total of, 128 possibilities. 0 through 127 is what that will give us. Makes sense, right? I hope that makes sense. So now what I'm going to do here is I'm just gonna clean this up a little bit. So I'm going to get rid of this here. So that's the positive number. So now what do we do for the negative number? Well, the negative number, it's actually really, really easy. That's why we're doing 2 tutorials. The negative number is the exact opposite of this. So for the negative number, it's just the complement of it. That's where the term kind of comes from, one's complement. So the complement, complement is basically the same as saying invert equals, think of it like this. Complement equals invert. All right, so all we do to make the negative -6 happen, I'm going to put it up here because there's more to come as we do this. So to make this 6 happen, I'm just going to invert all these bits. I'm going to invert the sign bit, everything. So this is going to be a 1. This is going to be a 1, a 1, a 1, a 1, a 0. We have a 0 here and a 1 there. So this is how this is exactly how we'd represent -6 in one's complement. So I'm going to put a 1 here. We have 4 more 1s. I'm going to try to line these up as best I can here. So we have 4 1s. We got 0, 0, and then 1. And I'm off. Oh, there we go. Okay, there we go. So there we go. So you can see. So it's kind of, I might rewrite this actually because you can see. So those are the 2 numbers though. So let me just rewrite this here a little bit. Clean this up just a little bit, guys. All right. So I hope this is all making sense. All right. So now what's interesting about this, because I used to wonder, like, where does the term one's complement actually come from? Well, the complement comes from the fact that we're inverting the opposite, right? So but if we were to add these 2 together, what you actually get is this. So what we actually would see, and actually I missed a bit here. I did miss a bit. I thought that looked kind of odd. So it should be 5 1s, 0 0 1. So all right. So if we were to take these numbers now and just add these together, let's do this. 1 1 0. What we get is this. So if we just add these together in binary addition. Now remember, binary addition, so I'm going to write the rules over here so we have it. So binary addition. If I can get this cooperating over here. The rules of binary addition. All right, hopefully you guys remember this. But if you don't, this is a good refresher. So 1 plus 0 equals 1. 0 plus 1 equals 1. 0 plus 0 equals 0. And 1 plus 1 equals 1. 0. So we basically do 0, and we're going to carry 1. So carry 1. We carry the 1 to the next column. The 1. Just like that. Okay. So hopefully this is all making sense. So 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 1 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 is 1. And 0 plus 1 is 1. So the reason it's called one's complement is because when we add the 2 one's complement numbers together, we get the complement and we get all 1s. So that's actually where this term comes from, one's complement. So that's one's complement in a nutshell. So now if I was going to read this, all I would do, like if I get that -6 value, so if I was to receive this number here. So if I get like 1, 1, 3, 4, 5, 0, 0, 1, all we do here is we have to identify which side is which. So this is our least significant side over here. This is our most significant side over this way. So all I gotta do is figure out which is my sign bit. So we now know that this is probably gonna be my sign bit over here. I say probably because like systems can do whatever they want. They don't have to follow that rule, but generally that's the way that works. So in this case, going to our rules, 1 is negative, so that gives us a negative number. And if it's a negative number, so if we get a negative number, complement the remaining bits. We complement or invert the remaining bits. Bits, just like that, right? So what I do is I read this bit. It says, okay, it's a 1 that's a negative number, and then we're just going to complement the rest of these bits. So in this case, we just complement the rest of these bits here. 1, 0, and that gives us our 6. So essentially, that's how you get back to your negative. So now this tells me this is a negative number, and this is actually supposed to read as 6. So pretty cool, right? Pretty cool. Now one of the disadvantages with this system is that if we were to add a really big value, like if we were to do some addition with this, and we start to go past our, like for example, if we were going to add two numbers together, if we were to actually have a carryover bit, we would have to subtract that and re-add that in, is what we'd have to do. So there's a little bit more to it. Where with 2's complement, we can actually drop the carryover bit, which is really nice. And I can actually show that here. So if we were to add, let's say, I'll try to find a good number here. If we were to add, like, let's go with -8 and 5. So let's say we want to add the values -8 and -5. Now we know, like, if we do some basic arithmetic, we know that should be -13, right? So that should be -13. That's what we should get to. So this is what we're going to try to get to. So what I'm going to do here is I'm going to make both of those numbers. So -8, and so let's make both those numbers first. So this would be good practice. So to make -8 in 1's complement, we're going to start with, we're going to do an 8-bit word. So I'm going to say 0, 0, 0, 0, 1, 0, 0, 0, and we're going to invert this. So this is 8 because 1, 2, 4, 8, 16, 32, 64, and this is 128 over here, so 128. So right, so that's positive 8, but we want -8, so we're going to invert this. So we're going to go -8. So I'm going to do 1, 1, 1, 1, 0, 1, 1, 1. So that's our number right there. So so what I'm going to do is I'm going to put this over here. So I'll put this over in the corner for posterity. So we'll say -8 is equivalent to 4 1s, 1, 2, 3, 4, 0, and then triple 1, 1, 2, 3. All right, so that's -8. And then we're going to do the same thing with 5. So we'll take -5. So we want to add -5. So we're going to do the exact same thing. I'm going to leave the scale, so I'm going to rewrite it this time. So this time we're going to do +5. So we're going to start with 5. So we need to start with the actual number first, and then just invert it. So 0, 0, 0. None of these numbers can go into 5. 4 can, so we're going to subtract. So subtract 4 from 5 leaves us with 1. 2 can't go into 1. 1 can't go into 2, rather. 1 can't go into itself, so we're going to put a 1 there. And this becomes our number for -5. We're going to invert this. So -5, rather, will be 1, 1, 1, 1, 1, 0, 1, 0. So this is one of the disadvantages now we're about to see. So here we have -5. That's equivalent to, we got 5 1s. We got 1, 2, 3, 4, 5, 0, 1, 0. Right. So there's our numbers. Right. So one of the disadvantages of this system now is, like, it's a little bit more complex to actually add the numbers together, and I'll explain that here in a sec. So if we were to add those numbers together, so what happens with this system is, in a 1's complement system, I'm going to write these numbers up. So we got 4 1s, 0, 1, 2, 3. We got three 1s there. All right, so 1, 2, 3. One more 1 over here. And then -5 is going to be like this. So we're going to say, let's see, we got 5 1s. 1, 2, 3, 4. So we got 5 1s. 1, 2, 3, 4, 5, and then 0, 1, 0 like this, right? So we're going to add these together. So if we were to just add these numbers together as they are, what we get is this. We get 1 plus 0 is 1. 1 plus 1 is 0. We're going to carry a bit. 1 plus 1 is 0, and we're going to carry a bit. 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 1 is 0, and we're going to carry a bit. 1 plus 1 is 0, and we're going to carry a bit. 0 plus 1 is 1. 1 plus 1 is 0, and we're going to carry a bit. 0 plus 1 is 1. 1 plus 1 is 0, we're going to carry a bit. 0 plus 1 is 1. 1 plus 1 is 0, and we're going to carry a bit. 0 plus 1 is 1. And you can see what's happened here, right? So now we're going to bring this one down. So now this one's way out here in the middle of nowhere. So with the ones complement system, because this is what we call a carryover bit. So that's a carryover. So we call it a carryover. Because it basically overflowed the register, or the byte boundary, essentially. It's an overflow, carryover bit. So what we do is we have to add that back in. So now I'm going to take, in another step, I got to take this 4 ones here, 0, 0, and 1. 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to add the 1 in over here, like this. And that gets us to our actual value. So to get to negative 13, so 1 plus 1 is 0. We have a carryover bit here. 1 plus 0 is 1, and we're going to bring the rest of the bits down. So 0, 0, 1, 2, 3, 4. Now, like magic, what we can now do is, if I rewrite this up here, so we got 4 ones, 0, 0, 1, 0. And if I was going to actually look at this number, again, this is, so what I'm going to, this is my sign bit over here. That's my most input side over this way. And this is my least input side over here. My most input bit is a 1, so I know this has got to be a negative number. And then we're going to invert these. That's our rule. We're going to invert these bits to get back to the original. And like magic, so what does that give us? Well, you can see here, so what we get is 0, 0, 0. So we're going to add, actually this might be a little bit hard to see. So this is the inverse, right? So what I'm going to do here is, let's rewrite this over here. So we got 0, 0, 1, 1, 0, 1. And if we add these values up, 4, 8, 16, 32, and 64. We add the 8, 4, and the 1, so 8 plus 4 plus 1 gives us 13. So that's how we get our negative 13. So we actually can get back to that negative 13. So as you can see, in this system, in one's complement, a little bit more difficult to deal with. Now, two's complement is very similar. So a two's complement system, I'm going to erase some of this now. So that's my tutorial on one's complement. So again, the takeaway here is with the one's complement number, a positive number, the sign bit is going to be a 0. The negative bit is going to be represented by a 1. The sign bit will be, if it's 1, if the sign bit is 0, it's positive. If the sign bit is a 1, it's negative. And if it's negative, we invert the remaining bits and we read it as is. If we're adding values together and we overshoot the boundary, then we have to add those values in. So that's like you saw here when we did the 13. So that's one's complement, right? So now two's complement. So now let's take a look at two's complement. A little bit. Now I'm going to use the same values. I'll just use the exact same thing. So I'm going to leave actually. So we're going to go with similar numbers. I'll use leave that. Get rid of some of this over here. Just cleaning up shop here a little bit, guys. I always say that. So now in this case, we're going to use the same thing. We're going to use positive and negative 6. In fact, let's just get rid of this too. And the rule is still going to be the same. Some of these rules will be the same. So like in two's complement, a 0 still represents a positive integer, and a 1 still represents a negative number. But there's one extra step, and that is if we have a negative number in two's complement, if the number is negative, if it's negative, we complement. So we're going to complement. So the first step will be complement the remaining bits, complement or invert them, and then we have to add 1 to it. So this is one of the most, two's complement, this is for two's complement, by the way. So this is, I'm going to write this down here, two's complement. There we go, so two's complement. So this is one of the most popular systems for representing positive and negative numbers. So if we look at like a positive 6, again, so positive 6 is easy. That's going to be the same thing. So in fact, I won't bore you guys with all that. So it's going to be a 0, 0, 0. So we'll still use that 8-bit boundary. So we got 1, 1, 0. That's our positive 6 still. So positive 6, let's see, that's positive 6. You can tell I'm tired. All right, let's just put that 0 back there. And then this is going to be positive 6. You guys are probably like, oh my god, she is tired. All right, so that's positive 6. So now how do we make a negative number for 2's complement? Well, it's going to be very similar. I'm going to take that number. So we're to make it in 2's complement, to create like a digit that's 2's complement, 2's comp. What happens is this: we actually take, we take the positive number, the 0, 0, 0, in this case 0, 0, 1, 1, 0, and we're gonna invert. So we're gonna invert just like we did before. So we're gonna invert these bits. That's our first step. That's like step 1. So this becomes 1, 1, 1, 1, 1, 0, 0, 1, and then we add 1. So the next step is add 1 to this number. So we add 1. So I'm just going to add 1 to this number here. So I'm going to draw a little box around it like this too, just to make it a little bit easier. See? So we're going to add 1. So we come in here, we're going to add 1 using binary addition. So this becomes 1 plus 1 is 0 with a carryover bit. 1 plus 0 is 1. Bring the 0 down here. And then we bring the remaining 5 bits down. So we got 1, 2, 3, 4, 5. So this number here is how we'd represent negative 6. So negative 6 is going to look like this. And what you'll find with this, with 2's complement system, is compared to 1's complement, one other thing happens, and that is in a 1's complement system, we end up with a negative and a positive 0. In this case, because we're adding 1, it's kind of twofold. So we only have, a 0 is a 0. There is no negative 0 in 2's complement, but also the carryover bit is no more. So when we start adding numbers together, we actually can drop the carryover bit in 2's complement, and it's very simple for addition. So with this system, in this case, if I receive this number here, so this is my number. If I see this number, I got 1, 2, 3, 4, 5 ones, 0, 1, 0. What I do is, this is my least significant side over here, most significant side over here. And to get back to what we started with, to figure out what this number is, we isolate our sign bit rather. So 1 is negative. We invert the remaining bits, which is like this. It's going to look just like this. And then to get back, we just add 1 to this. So we add 1 to this number, like this. So 1 plus 1 is, and again, I'll try to draw this out like this. So 1 plus 1 is 0 with a carryover bit. 1 plus 0 is 1. Bring the 1 down. And like magic, look at this. So we're back to 6. So negative 6. That's how we do it, right? So pretty cool, right? So now there's another little thing to this. So let's, what's one of the advantages of 2's complement? So now, before I actually erase any of this kind of stuff, so again, let me just summarize that. So the takeaway here is, in a 2's complement system, we look at the sign bit. If it's 0, like in this case, this is 0, we just read the bits as is. So in this case, this is 6, right? That's easy. If it's negative, like, so if we have a 1 in the most significant digit spot, and that indicates it's a negative number, we're going to invert or complement the remaining bits, and then add 1 to it, like I did there, to get back to figure out what that value actually is. So. Now this sounds like a lot. It sounds like really like a lot of like math and things like that. But there is an advantage to this, and I'm going to show you guys this right here. So we're going to take 2 numbers, and this time I'm going to take. Let's do. Let's see here. I'm going to leave this up here. So let's do like 8 and 5. So we're going to do. Let's say we have like positive 8. So we're going to do. In this case, we're going to do positive 8. And I'm just going to write the values up here this time, and then we're going to do negative 5. So what if we want to add, what if we want to like do some arithmetic? What if we want to like add these values together? So I'm going to convert these first. So this is going to be 0, 0, 0, 0, 1, 0, 0. I'll put the base 2 behind it. And then here we have negative 5. So let's a little bit of practice here. Let's make that happen. So we're going to make that 5 value because we haven't done that number yet. So again, we're going to start with our number. So I'll start with positive 5 first. In this case, it's going to look like this. So we're going to have 0, 0, 0, 0. That's the first nibble of the byte. And then the next nibble is going to be 0, 1, 0, 1. And again, I get this because if I add these values up on the scale, 4 plus 1 is 5, right? So just want to show you guys I'm not making this up. So now I'm going to invert these bits. So we're going to invert. So we're going to invert all these bits like this. Just like that. and then I'm going to add 1 to this. And I'm going to draw a little line here just so I can make things, so I know what I'm supposed to add together. So I'm going to add 1 to this to get our negative number. So 0 plus 1 is 1, and we're going to bring the rest of these values down like this. So 0, and then 1, 2, 3, 4, 5. So this is how we represent negative 5 in 2's complement. So 1, 1, 1, 1, 1, 0, 1, 1, base 2, just like that. And that's actually where the term comes from, because it's based on base 2. There's a whole article about that with 2's complement, like why they call it that. And I'll show you that actually before I stop this tutorial today, because I was curious, like, we talked about why do they call it 1's complement, but why do they call it 2's complement? Like, why do they actually do that? So, so now I want to add these values together. So this is where the magic comes in. So all I got to do to do this is I can just add these numbers together like this. So I'm going to go 0, 0, 0, 0, 1, 0, 0, 0, and we're going to add it to the negative 5. So so in this case we have negative 5 here. So all I got to do is add this bit. So I could just come in here like this. I'm going to go 1, 1. This is really cool. 4, 5, 0, 1, 1. So all I got to do, that's a negative number. All I got to do is add this together. Just add it together like this. 0 plus 1 is 1. 0 plus 1 is 1. 0 plus 0 is 0. 1 plus 1 is 0 with a carryover bit. 1 plus 0 is 1. 1 plus 1 is 0 with a carryover bit. 1 plus 0 is 1. 1 plus 1 is 0 with a carryover bit. 1 plus 0 is 1. 1 plus 1 is 0 with a carryover bit. 1 plus 0 is 1. 1 plus 1 is 0 with a carryover bit. And in this case, we get this little carryover bit over on the side here. But what's really cool about this system is we could drop the carryover bit this time. So in this case, this should be our number now. So what we have here, if I just convert this, so here we have 0, 0, 0, 0, 0, 0, 1, 1. This actually converts to the number 3. So this is actually 3 right there in base 10. And if we take 8 minus 5, 8 plus negative 5, we get 3. So this is the cool part about 2's complement, is we can easily add values together. All we got to do it doesn't matter if it's positive or negative numbers, we just add the values together, we drop the carryover bit, or the bit that, not the carryover bit, I shouldn't say it that way. We don't drop the carryover bit, we drop the overflow bit, rather. So this is what we call the overflow bit, so overflow. So we just get rid of that bit, the last bit that goes beyond the byte boundary, and we're down to our value. So it's very simple to implement, very simple calculations, and this is why, like, a lot of your engineers and stuff will actually use 2's complement over a lot of the older systems. So now I said I would, so that's the basics of 2's complement. That's the basics of 1's and 2's complement. I know this is a bit of a longer tutorial tonight. Now there's one more thing I'll leave you with, and that is, where does the term 2's complement come from? So if we actually do a little Googling here, I'll just get you this way. Why is it called 2's complement? So why is it called 2's complement? Well, the 2 in the name refers to the term which is expanded fully as an n-bit system is actually 2 to the power of n. So it's based on that 2 to the n power, which is where it comes from. So, and the only number that could actually be represented would be if you had. So what they mean by n is they're referring to the number of bits in the word. So realistically, the only number that could represent like a 2's complement, or the number 2 would be 2 to the first power. But that wouldn't make any sense because that would only be 1 bit. So a 1-bit system wouldn't work for positive and negative numbers. So that would never be a thing. So because we have to have more than 1 bit, right? So, but that's actually this is actually where the term actually comes from. So, and there's some really handy like articles on this kind of stuff. So if you're interested, I highly recommend looking into it. But I hope that this gave you guys a little bit of a nice overview of 2's complement. I hope so. And I'll see you on the next tutorial. So have a good night. Have a good weekend. It is Friday. Happy Friday. And thank you for joining me on the tutorial. And I'll see you on the next one. Until then, happy Friday and toodles.